Hi there, Team RoverX, based at Creation Labs, Vellore Institute of Technology, India, is a team of 30 undergrad students working on their Mars rover prototype. We participated at the European Rover Challenge twice, and this is our first attempt at the University Rover Challenge. After several months of hard work and dedication, we are excited to unfurl our latest rover for URC, Ares. The focus of this year was to simplify the design, have onboard backup systems, and ease of control to make sure tasks are completed with ease. Here's an overview of our overall system design and functioning.
The mechanical team worked together to design, manufacture and assemble the external component of Ares.
The chassis has been designed with a factor of safety of about 3 to withstand the extreme loading conditions.
The suspension of the rover is a 3-rocker system consisting of 3 independent rockers with a 6-wheel drive. The rockers are designed keeping in mind the conditions the rover will have to traverse through at the MDRS during the extreme retrieval and service task. The 3-rocker design is simpler and optimized when compared to the rocker bogie as it reduces chances of mechanical failure. The base area is kept wide, the ground clearance high. However, the center of gravity is kept low by using base-heavy motors to counter toppling while climbing steep slopes and performing the 1.2-meter drop with the robotic arm mounted. Turning mechanism used is the differential system. The rover turns by regulating the RPM of the wheels.
The robotic arm consists of a base plate assembly and 2 aluminium alloy tubes which make up the major links. The base plate assembly is designed to withstand heavy loads and bending moments. Linear actuators and DC motors driving spur gear trains are used for actuation of the arm.
The focus of electrical subsystem this year was to reduce circuit complexity and the battery management, keeping in mind that rover should work for maximum of 70 minutes during the extreme retrieval and delivery tasks. The batteries on the rover can keep all the systems running for maximum of 90 minutes, hence providing a buffer. The decentralized power distribution on the rover helps in reducing the overall wiring throughout the rover. This in turn makes other subsystems of the rover easier to debug and assemble at event site. Customized control boards using Atmega 328P are used. Improved safety mechanisms have been embedded which are not available on off-the-shelf control boards directly.
The control boards give the necessary feedback to give the rover status. Current and speed sensors on board send actuator configuration at all times. In case of extreme malfunction, particular subsystem can be electronically disabled by the driver in addition to an onboard kill switch. A Raspberry Pi is used as the main controller on the rover which communicates with the base station over the ROS framework. The communication from the Raspberry Pi to the Atmega 328P control boards takes place over the I2C protocol.
We are using 2.4 GHz 300 Mbps off-the-shelf Wi-Fi routers to communicate with the rover. A directional antenna is used on the base station and an omnidirectional antenna is placed on board the rover. The command station antenna tracks the position of the rover at all times and changes orientation to maintain connectivity. Rover vision also operates on the 2.4 GHz bandwidth and provides a constant 24 fps tested till a distance of 1 km. In case of interferences at the 2.4 GHz bandwidth, the rover self-initializes an FPV cam placed on board which operates at a 5.8 GHz bandwidth, which will help us to complete the task successfully.
The autonomous navigation is achieved using sensor fusion, image processing and neural networks. Long-distance waypoint navigation is done using a GPS module and 3-axis magnetometer. Obstacle avoidance is done using LiDAR and neural networks are implemented using TensorFlow and Keras. Marker detection is achieved using image processing and a camera module. The image processing algorithms have been implemented using OpenCV and Python.
For the science caches task, to determine the habitability of the site, our strategy is divided into site selection, documentation, sensor data acquisition, sample caching, and laboratory analysis.
For accurate soil investigation, we are using digital microscope which is mounted over the soil box. For sample site selection, images from the panoramic camera, soil and cliff images are examined using image processing algorithms. Our drill operates on Archimedes screw principle which displaces soil from ground to be stored in airtight cache.
The robotic arm can be moved to preset locations on the rover such as the soil box and tool storage box using forward kinematics.
Image samples are calibrated using spectroscopic data.
The rover is equipped with sensors to obtain information regarding the site like temperature, humidity, wind speed, pressure and gas composition. The soil is analyzed using gas sensor, digital pH probe and temperature and humidity sensors. In the lab, soil is tested for presence of life-determining elements along with traces of microbial life.
The rover is equipped with a two-link end effector which will be used to complete the servicing as well as the retrieval task. 4 sensors are placed on the links to obtain data regarding its configuration. IMUs and actuator feedback give arm configuration at all times. These features make sure the object does not slip from the end effector and help the driver in completing tasks with even a distorted camera feed.
The management team is responsible for keeping the project on track. The team will be starting its crowdfunding campaign in early March to support its financial needs.